Determine the force in each member of the truss. State if the members are in tension or compression. Since the question asked to find the force in each member of the truss, that leads me to believe that I should use the method of joints because we're solving for each member. That's not always the case, but more often than not it is. If they want specifics, then I would use the method of sections. So here we're going to use the method of joints. I went ahead and I located the zero force members in this truss. There's only one, and it's BC. I had it circled, but I guess it got erased. But see, yeah, BC here. That guy is a zero force member, and I drew the free body diagram at joint B to clarify this, in case anyone couldn't see it. You know that the sum of the forces in the x and the sum of the forces in the y, they must equal 0. We only have BC acting in the y, so that means BC itself must be 0 because we have no other force to counteract it to sum up to 0. But we do have AB and BD in the x, so these can't go in the same direction or the body won't be rigid. So they must oppose each other to maintain static equilibrium. Moving on, let's go ahead and identify our support reactions. Let's notice this 130-pound force on the left side of our truss. I like to break them into their components because, well, some people like to, for their support reactions, they'll just guess the direction, and there's nothing wrong with that. But I like to try and deduce what direction they'll be going. So I'm going to call this force T, Tx, and Ty. So a roller at E, you know it produces a normal force on the body. So I'm going to call this EY because it's in the Y direction. And then looking at our X component of T versus the support reactions at F, which is a pin, we know it's going to have a support reaction in the X and the Y. That'll be our only other X reaction force in this total system. So it has to go in the opposite direction of T so that our sum of the forces in the X maintains static equilibrium. So if Tx is in the negative X, Fx is in the positive X direction. Now you could just guess for Fy, but looking at this diagram, I know there's a pull this way, which means that there would be a pull here going up. So that means your y direction needs to counteract and cancel that force. So Fy will go down. Alright, now that we have that, let's go ahead and find our system's equilibrium or global equilibrium, the whole body. Alright. So the sum of the forces in the x direction equal 0 equals Fx minus 5 over 13 times 130 from our slope triangle for a 130-pound force. And Fx is going to be equal to 150 pounds. Sum of the forces in the y equals 0 equals positive Ey minus Fy minus our y component of our 130-pound force. So that's going to give you the equation that Ey minus Fy is equal to 120. Solving for the moment about F, which you can choose about where you'd like. I'm going to do about F. That's going to give us negative 3Ey. And I'm sorry for this video if you're not very familiar with moments and the directions, but if you're on trusses and statics, I'm going to assume you know them, so I won't cover them. But if anyone would like a more in-depth video on them, then just comment it below. And I'm sorry if it inconvenienced you that I skipped over it. But solving this moment equation, you get Ey equals 360 pounds and plugging this into here, that would give us the Fy equals 240 pounds. Cool. So now that we found global equilibrium, we're going to go ahead and start analyzing the joints, which I'll copy and paste this because I know some people like to be able to see it as they work the problem. So let's do the free body diagram at joint A, because for the method of sections, we can't use the moment because you can imagine if you go ahead and let me just draw the diagram for A. That's AB, and we have this 130-pound force with the slope triangle, 5, 12, and 13. Then we also have the force AC, and we'll analyze for direction and all in a second, but what I was trying to say was, imagine taking the moment about that. It doesn't work. So therefore, the equations of equilibrium we have to work with are Fx and Fy. If we only have two equations, we can only solve for two unknowns. So for the method of joints, we cannot have more than two unknowns at our joint. That is why I chose A. You could choose F as well, but that is more, I don't know, I just wanted to choose A. So we're going to do A. Now looking at this, you can see that our 130-pound force has components going in the negative y direction and in the negative x direction. We only have one other force, which I'm sorry I didn't label it, it's AC, that has a y component, so it must counteract the negative y component of the 130-pound force, so it has to be a positive y component. This will only happen if this is a compressive force here. And let's go ahead and draw our slope triangle for that. You can see up here, AC is right here. This triangle is 3 feet in the horizontal, 4 feet in the vertical. So the slope triangle is going to be a 3 by 4 by 5 triangle. And then AB. So both of these, you can see now this has, oops, sorry, I meant to draw that in a different color. The x component of AC also goes in the negative x direction, so AB must go in the positive x direction, because both other forces go in the negative x direction, and we need it to counteract that. So let's go ahead and do our equation of equilibrium for this problem, or this free body diagram at joint A. So the sum of the forces in the x equals 0 equals the x component of our 130-pound force, which is just going to be 5 divided by 13 times 130, and the negative x direction will give us negative 50, plus a positive AB minus 3/5 AC. Sum of the forces in the y equals 0 equals our y component of our 130-pound force, which is negative 120, plus 4/5 AC. AC equals 150 pounds, and AB equals 140 pounds. That's what you get when you solve this equation, or the two equations together, the system. So it also asked if the forces were tensive or compressive. So looking at this, we see that AC is pushing in right here on the joint. It's compressing the joint. Think of it as CPR. You're doing compressions. You're pushing in. So AC will be in compression, is a compressive force, and AB, it's tugging on the joint. It's pulling away, so it's tensive. Alright, I'm going to go ahead and check these off. We have found AB and we have found AC. Sorry. Okay. Now I'm going to do a free body diagram at joint C, because remember, you can only have two unknowns, and so joint C, we don't know CD and we don't know CE. Remember, the joint BC, we know this is 0, so I'm not going to include it in the free body diagram at joint C. Alright. So, joint C. So, C, I'm not drawing BC, remember, because it's 0. We need to find CD, and we need to find C. Sorry, that's purely horizontal. A little slanted. Okay, and AC, remember up here we derived that it is a compressive 150 pounds. So, compressive, if it's pushing on that joint, it's going to push on this joint as well. It's still compressive. And remember, it had a 3, 4, 5 slope triangle. Looking at CD, it is also a 3, 4, 5 slope triangle. It's convenient, nice. So CD is the only other force acting on C that has a vertical component that could counteract our AC force. Because CAC is going down in the Y in positive in the X direction. CD is the only other one with a vertical component to counteract that, so it means that its vertical component must go up, like so. So it's a tensive force. That being said, now both AC and CD, their X components act in the positive X direction, which tells you that CE must act in the negative X direction. Doing our sum of the forces in the X direction, we get 0 equals the X component of CD, which is in the positive X direction, plus our X component of AC, which is just 150 times 3/5, minus CE. Our sum of the forces in the Y equals 0, equal our Y component of CD, minus our Y component of AC, going in the negative Y direction, 150 times 1/5, negative 120. Solving these equations, we get that CE equals 180 pounds compressive, because it's pushing on the joint, and then CD equals 150 pounds tensive, because it's pulling on the joint. Now, we're going to see, what have we determined now? We know AB, we know AC, we know this one, BC is 0. We have now derived CD and CE. I'm going to choose to do the free body diagram at E now, because we know this force, the EY. We said that EY equals 360 pounds. So immediately we can see, doing the free body diagram at joint E, oops, sorry, I didn't mean to draw the arrow. ED EY equals 360 pounds, positive Y direction, and then we have, this is kind of in the way. Okay, and this is just another 3x4 by 5 slope triangle for EF. and this is CE. And remember, we just found CE. It's a compressive force of 180 pounds. So the only other force that has a horizontal component is EF, and it has to counteract the horizontal force at CE. So it has to be a compressive force. So that way, the horizontal component goes in the negative x direction to counteract the positive x direction of CE. Alright. This being said, you can take a guess at what direction you think that DE, ED, whatever it's going to go in. I'm going to guess that it will be a compressive force. Doing our equations of equilibrium yet again, we have in the x 180 minus the x component of EF. This tells you that EF equals 300 pounds, and it's pushing on the joint, so it's compressive. Now the sum of the forces and the y equals 0 equals positive 360. I'm not going to draw the pound. Minus ED in the negative y direction. Sorry, I don't like to draw my e's like that in math. Looks like a 3. Minus 4/5 EF, that's the y component of the force EF. And we just found that EF is 300, remember? So let's plug that in. That lets you solve for ED, which is equal to 120 pounds. And it's a compressive force, it's pushing on the joint. Now, lastly, I think we're getting down to the last of it. Thanks for sticking with it, but found this, found this, found this, found this, found this, found this, found this. We just need DF, that is all. So let's do joint F. Alright. So at joint F, remember we have the support reactions, yeah. And we found them to be 50 pounds in the positive x direction and 240 pounds in the negative y direction. We still have Fe, which we found to be 300 pounds compressive, so it'll be compressing the joint. 3/4 slope triangle. And we also have one more joint here, the one we're solving for, DF. You can see that both our horizontal components that we have so far are going in the right. So DF must go in the negative x direction. Let's sum our forces in the x direction to find DF. So negative DF plus 50 plus 3/5 times 300. DF equals, thought there was a negative there, sorry. DF equals 230 pounds tensive force because it's pulling on the joint. And I think that's everything. And if you look up at the original free body diagram I drew for BD, and there's AB. AB is tensive, and we said it's 140 pounds. If AB is 140 pounds tensive, this also has to be 140 pounds, so BD is also 140 pounds. BD equals 140 pounds tensive. So that's one of our answers. Sorry, that looks not awesome, but whatever, you get it. BD is 140 pounds intensive. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 members. So it's 1, and then 0 force is BC. BC equals 0. That's 2. Then we have AC and AB, 3, 4, 5, 6, 7, 8, and 9. Yeah, we've got everything done. Great job. Thank you for watching.